other people did. But I haven't been in India for 2.5 years because of COVID travel. It's been on, sad. I like coming here. It's been really good. I spent a lot of time working with AMD team and the Intel team, and many hours working on some pretty hard problems. Odd not to come on a regular basis. And then we did a tech talk at
Sorry about that. Please go ahead.
There you go.
Yeah.
I see. Are we going to have a theme during this whole thing? We'll go back and forth. We had a really fun night. Talking like a couple weeks more. And then yesterday we were talking. Today I'm in Peru. Really. And I'm talking to you guys. So, how many people here were at the biggest? Anybody here work on Graceful and Wormhole? Couple more hands. Hey, by the way, thanks everybody. Great work. You helped build three, there was, I guess, we call it Chalk Ridge. I always forget what the first was. Yeah. And then Graceful and Wormhole, they all work first pass. That was fantastic. It's really good work. And the test works, the chips work, VRFI, everything. There's little tweaks here and there, but it's amazing how well that worked out. So I really appreciate it. How we're working on the third big part together, black hole. So yeah, I wanted to come here and meet some of the people that work on that. Talk to the guys in the front row here. Nice not to. Nice. And then I told you, Judy, I've been working on a tech talk. Excuse me, yeah, my friend. Please, can I get rid of this? Yeah, and then how do you change slides? That's like a touch screen. And so I'm going to talk about a bunch of different things, a little bit of computer history, a little bit about how we can design, I'm going to give some examples, and I'm going to talk about a new processor we're building, and then some interesting things about AI. But if people have questions at any point along the way, please shout them out. It makes it kind of fun if you want to interact. And this reminds me, so I used to work at Apple. And I didn't work directly for Steve Jobs. I worked for a guy named Mike Colbert, who took the seat multiple times a day. And one of the reasons Steve did it much better his second time at Apple was he's a very difficult person. So he picked like 20 people that he talked to, and he was both very, let's say, inspirational and very tough on them. And one of his things was when he was building an iPhone, Mike would come in and pantomime Steve, because he talked to Steve so much. He said, Steve said, silky smooth, silky smooth. So when we were making like the original, I worked on the third, fourth, fifth, and sixth. Those third, fourth, fifth, and sixth generation iPhone chips. And getting the screen, the scroll, silky smooth was really, really large, especially when we had for the high-res display. And there was a really funny thing, and this is where you learn these eyes less. So at Apple, when you scroll the screen on the phone, if it wasn't fast enough, it didn't render the pixels. It was old enough to remember to put a little pattern on, so the movement was correct. Whereas on a Windows phone, it would render the screen and then stutter the movement. And if anybody's ever dropped anything, it gets a little blurry, right? But it always hits the floor at exactly the same time. So Apple decided that physics was more important than that look. Because it was fascinating. I think they were right. But the way Steve described it, still here in our heads as we're trying to do that. We knew if we didn't, there would be hell to pay. He was not one of these guys who said, "We'll do the best we can." No, he never said that. So yeah, he always said, "Do the best you can, and do it," or die trying, or so. So smooth, but not bad. All right, so I'm going to talk about a little bit of history of computers, abstraction layers, and one reason I'm talking about this is we've done a lot of work in the last year and a half, so I joined it before that, on really understanding how the layers of software and AI work. And it reminded me that understanding how that works is super important in design. I'm going to give an example, like simple example for IT and SSDs, and I'll talk about CPUs and our which five processors we're building, and then something about AI software and hardware. And then I have a picture of our cloud. And I'm just showing those because I'm
Switch the speaker. Speakers on. The speaker to be.
One more little question.
Excuse me. Yeah, please.
We get rid of the fact that the top so that slides. This is the weirdest thing. I'm a computer architect. I've done a lot of programs, like a lot. Back in the day, I used to program. I used to be really happy, like on Saturday. I'm not really that good at computers. Like I always, how does this thing work? Why does it?
Turn off the speakers.
I think I might get stuck in the games. Like I really knew how computers work in the 80s and 90s. Remember Unix?
Yeah, this is working amazing. Even when
just the one. Oh, you're talking about.
all they have to do is just.
There's a button on that. Oh, we're replacing that. Why is it? What's that? That's a pretty dynamic place.
No, sorry, you're not able to hear all the lights on the cast properly.
Here it is.
Light in.
Yeah, really?
Yeah, it is becoming an issue. Multiple
Complaints.
No way. I hate these. You want to try this, huh?
You're making me feel. That's even worse. Yeah, so. Does this one work? Yeah. I do too. Yeah. Do you agree?
Reset. Yeah, online's becoming an issue.
Is it on?
Ladies.
How close to it? Oh, we're switching. How about this one?
Are you guys able to hear?
Can you hear?
Yes, yeah. Okay. Can you put on the chat?
Can they hear on mine?
Yes. On the chat.
We're checking something called chat. I was at TENSTORRENT for 6 months. Somebody said, no, everybody uses Slack here. Are we going again?
Just waiting. Everybody.
Yeah, go ahead.
So yeah, no complaints so far. So.
Guys still look like a SAD super agent force or something. You look cool, but it's a little cringe. Usually I say, like as a leader, like I feel like if there's like a team of 20 people and they're not doing what they want, what I want, we're gonna figure it out. Either, I'll straighten them out, or I'll figure out what's going on, or maybe it's neat. But I usually feel like a 20-to-1 ratio is how you.
This is too hard.
But you guys, I don't know, it's like 40 of you. It's very. You can hear someone else too. Okay. back to my talk. What wasted of time. So that's a picture of an X8800. That's the computer I worked on back in 1986. That's where I learned to use Emacs and my C programs. And we built computers back then that ran in C programs fast, but that was our goal. Back on it, that was a $500,000 computer, 150 people, 4 years. We built it. Probably slower than the computer in this microphone. A little tiny. That's what we built, and we're proud of that. That was good business. I think we sold $10 or $50 billion worth of vaccine. Right, and Gordon Bell was the CTO, and they made something called Bell's Law. Right, and he said every 10 years, so you get enough transistors to make a new kind of computer. Right. So mainframe, mini workstation, PC, mobile, like that was the progression. And that's what I worked on for years. I worked on many computers, workstations, PC, mobile, and we saw them as really different kinds of computers. But to be honest, they really all run assembly line code, and they all run C programs. And even though today we have higher level languages like Java, JavaScript, all the things, if you look down at the bottom, it's the same computers. Now they happen to be about 10,000 times faster, but it's the same kind. And I'll circle back to why that's important when we get to AI. That is a low resolution picture. All right. And I really like this when I'm giving some talks on Moore's Law. And people frequently say Moore's Law is dead, but a friend of mine, Pushkar Ranade, I worked with him at Intel, he pointed out that the Apple M1 Ultra is right on the curve. And this is an amazing thing for what it's at. 50 years, it's a steady increase in performance and transistors. And the number of transistors we get lets us go faster than computers, but it also creates complexity. Like it used to be a simple 2-3 stage pipeline. One person can figure it out. And in today's tools, one person can build that computer. Right? But a modern out of order computer, takes somewhere between 100 and 200 people. And the complexity. And the reason it's complicated at some levels because we get more transistors. And human beings aren't getting smarter. And you can't just throw the team 1,000 times. We'll never finish the project. So we've had to get really much better. Somewhere in the mid-'80s, somebody published this thing called networks. Right? And it was fascinating because I was at Digital and we were building something called TechNet Phase 4, which was shipping, and they were working on TechNet Phase 5. It was a very complicated new network architecture, software stack, transport layer, everything. And TCP/IP guys defined separate layers: physical, data link, network, transport. Genius of it was the layers were really easy. You could innovate on one layer without having to reach on the other. In TechNet Phase 5, they just kept working on the definition. Meanwhile, TCP/IP shipped and took over. And those layers were being refined a little bit over time. Don't do that, please.
You need like
Go turn.
Infinite line coming. Straight. One light. Yeah. Your screen has some lights. That's why I found. I can't see anything. Sorry.
There's going to be, you guys need to use 45. At Apple, they did keynotes every year. And then when they did go well, Steve was supposed to stop. And the word was the more you throw, the better the keynote. But if somebody turned the lights down while he was talking, or the light faded, there would be hell of it. It was a little weird, to be honest, but also a really good lesson in professionalism. want to do something great. Every little detail counts. So I thought this was really interesting. Right. And then every once in a while, I'm working on a problem, working with a group, and I realize they have it really properly defined all the layers, and the people working on it won't know which part they're working. And then things go sideways. And layers show up all over the place. Modern semiconductor process have between 60 and 80 layers, but really inside each layer, there's this thing called deposit material, polish it, pattern, etch it, repeat. There's a loop there. And sometimes you deposit, polish, and then clean. There, when you do patterning, sometimes there's a couple of steps to align several different masks, and then you etch it. And then if you go to Wikipedia, there's a whole bunch of places you can see the way, like there's variations in these patterns, steps. For a modern process, this ends up being about 8 steps with 80 layers, that's 640 layers, right? And they don't solve that all at once. There's different groups working on different layers. And they're, like a transistor stack, the low level metals, the high level metals are very independent. And getting that independence is key to making. So I was looking for who made up this quote, but it might be me. Complexity is when you have too much stuff in one spot. So there's probably some young engineers here, and you think this is so hard, I don't know how to do it. You have to break it down. Nobody, jumps to the top of the mountain. You climb up one step at a time. Nobody learns a hard thing all at once. And engineering design, you don't really solve big hard problems. You break it down, focus on the problem. And whenever something's hard or really complicated, it's either not factored in the layers properly, or there's too much crap in one spot, and you have to take it apart. And that process is what lets you do really great design. So I'm going to use this layered stack to talk to you now. So modern computers, we typically think there's an application like you're running Linux. There's an architecture that implements it, the reference model where you emulate it and make sure you have a complete definition. The performance model maybe attached to that, so you can see if it's really going to hit your performance targets. Then you build the microarchitecture, verification plan, and then you do implementation. And this stack was hard when we first started building computers a long time ago. We'd figure out the architecture and then jump to the implementation. And later on, hire some people to do tests, and then we start debugging. And the methodology of building this stack and working through it, having different people declare, really, really important. I just wanted to point out, sometimes, like down under the implementation, there's even more layers, right? And in a group of 100 people, you often find that each one of these has multiple people, but they make the expertise in each one. And the interesting thing is, have you factored that properly? It's about the subtle variations I do it. Does everybody know what part of it they're working on? Like between these guys and these guys and these guys, do they know what they're doing? Are they talking to each other properly? But also, can they do their work? Really an interesting process. And then, like I said, I'm an architect. I also manage small and large teams. And it's interesting to architect a team so they can tactically solve the problem. But also architect the design so that pieces can be done. Like people can own their own stuff and be independent. It's really awesome. That's what does that one. Right. A simple IP example. At a startup back because SciBite we did it. We built a PCI trust controller. I think it's Gen 1 or Gen 2 with 3 people. One person did the controller, one person did the PHY, one person did the verification, and then we built it for work. Now, it doesn't seem complicated now. But, a modern PCI trust controller, talking to a cache coherent bus, there's a massive controller, probably a buffer manager, maybe it's a reliable server part, so there's a big link error management widget. The PHY itself is actually the digital part is literally a supercomputer doing simple processing, and then the analog part's a little complicated. And then you better build some kind of powerful method for verification so that each piece can be verified. And then there's a reference model and possibly performance model. And Intel did some investigation and found out there was 5 different teams working on one of these but the implementation of this, but the performance is way higher, right? So you're doing 30 gigabytes of bandwidth, the 500 nanoseconds of memory latency with multiple screens and high reliability. Every single piece of the problem is really hard. The people building it are way smarter than the way back. But we fraction that problem into lots of pieces and then properly layered implementation, verification, reference model. You can successfully build, like we licensed the defect trust controller for very slow wormhole, plugged it in, and it basically worked. Fascinating. You can even buy a 5-for-1 company and a controller with another company. So plug it with AXI, it's a large AXI knock interface, and the whole thing will work. You know, probably 6 countries involved, multiple pieces of IP, and that discipline of building the same work. And then at the SoC design level, if you're solving problems at the top level SoC, you've done something seriously wrong. At TenStorrent, the way we built this is the memory controller has a inside this block has a PHY, a controller, and an interface to or not. We built that as a physical partition. You know, there's a CPU block, there's an AI block, which we'll talk about later. These are addressed the same way. PHY, controller, and then there's a knock interface. So the top level SoC assembly, the first time I looked at it, it was basically not clock scan. Really nice little glitch here. And that's why you execute the blocks properly, then you can execute it. So I worked on Zen 3. Well, we go from VAX 8800, which has about probably 100,000 transistors in it, plus about a megabit of DRAM, to Zen 3, which is hundreds of millions of transistors. They're the same kind of computer. The thing that's radically different is we went from non-pipeline, pipeline, super pipeline, the super scalar, and then to out of order. What is it? All right. I hope you debug this on your first pass. You need it later because the touch stick doesn't change it. What's that?
That one also is there, but it does not test it.
There's a rule. You don't test it, doesn't work. I used to think you could build stuff and don't overrun test later. Boy, if you don't test it, nothing works. Especially in the modern world. So we managed the complexity going from the simple non-pipeline computer to a modern out-of-order computer by building these layers. And there was a point in time when we first started building out-of-order, quite a few people in the industry didn't think we could ever solve that complicated problem. You remember the same company called VRW, and for a little while there was an argument like which one was going to work. And what happened was the VLAW compiler to go fast. That team grew so much. At one point, there was 1,000 people working on the compiler, and we slowly cracked with all of that with execution. Intel internally had an out-of-order computer with a very small team that ran faster than like a that's an example of it sort of violated the layers. up in the software application when it piloted, they said we're going to try to make the hardware microarchitecture run fast, and that was a complete fail. All right. So when we build a CPU, and we're building a new CPU, so we started this process. Right? The application layer, what are we doing? We're going to run Linux, we're going to run vector code, we're going to run AI code, we're going to run schedulers for AI code, we're going to do some network processing, we're going to do some accelerated storage processing. There's a couple of applications, and that's set like the bounding box for what we want to achieve. The architecture that we came up with, which I'll show you the slide, is we want a really high spec integration because we're running lots of random C programs, high floating point rate with large vector units. We actually defined some new AI data types. We need cache coherency of 1.2 cache, so we can have many processors cooperate on some of these problems. And then to build that, RISC-V has a reference model called Whisper. We put some extensions in that. We added tracing. We added some interfaces to the reference model so that we can easily hook the reference model up to the performance model and verification environment. And then we build a performance model that's tightly coupled both the reference model and the core architecture. And then at the architecture level, that's yielding this. So we're building a CPU team in Santa Clara, Austin, and we start open an office in Bangalore, where we're going to build an 8-wide out-of-order computer. RISC-V is really cool because it's a modern and really well-defined architecture. So they defined it in layers. There's 64-bit definition, atomic instruction extensions. There's some compressed instructions, double precision, single precision, vector unit. And then from the performance model and architecture spec, we define all the features we need, one size integration. So we have this pretty solid architecture model, and then the team has got that performance model. Just to point out, the RISC-V was started by David Patterson and some students, and then Krista at Berkeley. I know those guys. They built as students 2 cores, one's called Rocket, one's called Boom, which are open source and available. We downloaded those processors and hooked them up and run them in our environment. We also built a smaller processor called Baby RISC, which is in the TENSTORRENT parts that work on. And now we're building a really high-end processor. So RISC-V is pretty much the top of box stuff, which is cool. And then there's companies involved in this: Sci-Fi, Ventana, Revos, TENSTORRENT. And by the way, they're all in India. Well, and the thing I really like about RISC-V is when we were defining Blackwell, we looked at ARM, and then we asked them if they would actually point what data types to us. So they basically said no. But we don't see a market need. We said, well, we're a market need. Guys over here, they're texting each other. That's easy. But when we called up Sci-Fi, we said, hey, you have this floating point construction, we'll put it in the next drop. And RISC-V right now is like the space where people are really working on new architecture. And that's what it was RISC-V to get ahead of the rest of the competition. When we're designing a new processor, we have the opportunity to think about how we put it together. What used to happen is you define the pipeline, and then to make the pipeline go fast, and also to be really efficient, you sort of hyper-optimize all of the layers. And you need lots of wires, especially doing that to be hard. But then when you go back to verify, you get 100 wires and all wheeling around ad hoc definitions. Really hard to do. So we started at the mark architecture level. Each unit we want to define independently and have the smallest number of interfaces. They're both carefully defined. And this is an example of having the verification of the design and the complexity of the interface work together. CPUs are getting so big that if you had to we used to be able to build a processor and then verify it as a whole CPU by running programs on it. You just run more and more programs to verify it. Modern designs are so big, you have to do that. You could never hit all the corners. We've broken the process, like the front end has an instruction interface, a memory fetch interface, kill interface, PC redirect interface. Each one of those is really well defined and hooks back to the program. We should be able to test that unit fully independently. And then we put it together and we'll see if we can like we've achieved this kind of stuff at SoC level, where you can have a fabric, CPU, and controllers. You don't expect to hook the CPU to the fabric with the PCI Express and find it through the bug. We're trying to go through the same process. And here's our microarchitecture. This is a very modern, out of order design. It's 4 stages in fetch. Then there's an instruction pipeline where we line the data and do the decode. And then there's the register renaming path. Then there's the scheduler where we pick instructions out of a very large instruction window. And then there's the execution. And it's always interesting because vertical computers are relatively unpipelined, and then the risk guys came up with a standard 5-stage pipeline. Fetch, decode, register, read, execute. All this stuff getting to the execute stage. The 14 cycles of work before we get there. You can almost even think of each one of these color-coded blocks as a separate computer that's independent. That's the level. So not only kind of layer the design from the architecture down to the implementation, we define the processor in terms of pieces of the really. This is why we feel complicated in modern place. And this design, we sort of have this part of the machine up and running, and then we're starting to build out the team to go build the rest of it. That's it. Just a quick list. Some designs people work on iterate, like Intel and AMD, so we have one for. But what they frequently mean, they add features to the world for. Some of those designs are can't. Everyone's like a chance to go do a new design. And when you do it, super important to do everything you can to make it at the highest standard. So approval interfaces, really scalable definitions. We're building new data types for AI. We're going to explore how CPUs and AI processors talk to each other. We think that the collaboration between AI computers and CPUs is really important. And one of our plans is to learn as much as we can doing it. So all right, I'm going to talk about AI a little bit. So one of the really interesting things is another way to interpret the Moore's law curve is as we got more transistors, it enabled us to go build more complicated things. Like the reason we didn't build an out of order computer down here is we just simply didn't have enough transistors. And as we got more transistors, we went from non-pipeline to pipeline to out of order. Right. We started to build GPUs somewhere along here, but it took a while to have enough transistors that you could build something called a shader, which lets you run a program on every single pixel that goes through the machine. Right? Any gamers in here?
Can you take the mic closer?
Okay. Sorry. Yeah. If there's any gamers here, back when they were doing texture maps, when they first started texture mapping triangles, it looked good, but with texture maps, you couldn't really make it look realistic. And at some point, they were putting 8 texture maps on a pixel, and it just started to look blurry and everything, and then shaders came out, and it was a whole different world, because they could really do lighting, translucency, transparency, all kinds of things correctly. That was enabled by transistor count. And then we also enabled multi-core processors. When we did K8 at AMD, our original proposal was we were going to go 4 processors on a dot. We defined the architecture of the bus, but Everybody said it was crazy because at the time, there was one processor could only fit. We got a process straight, we got the 2, then we got the 4. Now we're talking about 64, 128. Right? And that's enabled by transistor count. Jeff Dean did a talk at DAC last year. He said there was a time when they started to get some AI programs to actually work, which was some insights into math programming. They were trying to scale it from 1 CPU to 64. They did all this work to scale to 64. And when they were done, they realized it was still a million times too slow. So the AI revolution that we're starting to go through is partly because of some work people did in what they call gradient descent backpropagation, convolutional neural networks. There's a bunch of features like that, which were, say, mathematical innovations and algorithm innovations. But the thing that enabled AI to be practical was the transistor count and the high density compute. But even today, like the big language models, this is an amazing number. Take 1,000 to 10,000 GPUs a month to train. Nobody really wants to train something for a month, but that's, I say it's a high-end AI still. But the transistor count let us build something called. So we made a slide when we were raising money. And we decided that quoting under Kirkpatrick is a really good way to raise money. So if anybody's raising money, he's the guy to quote. But he said there was 2 kinds of computers. Software 1.0, people wrote programs, right, to do what you want. And there are C programs, and you kind of write them in steps. Do this, do this, do this, do this, right? And I personally spent 40 years making C programs run fast. Way back in the day, they run like 1 instruction every 5 to 10 cycles. Right? Now, a modern out-of-order computer runs 3 to 5 instructions a cycle. So all the work we did to go pipelines out of order speeded up the processor about 25 times. We also raised the frequency from about 20 megahertz to about 4 gigahertz. Right, for 200, that's a pretty nice speed up. Right, but it's the same kind of program. AI is completely different. You use data to train models. An AI program does not run like somebody's had over steps in their code. It runs in a completely different way. These kind of computers are completely different. And then, I don't think like you read any AI papers. Right, I want everybody here to start reading through AI papers. It's really interesting, as wait a minute, you guys aren't reading AI papers? I thought you worked in an AI company. Oh no. You guys really are secrets. Here's a really interesting thing. So there's thousands of people now working in AI research. They write a lot of papers. And they're actually fairly interesting, but I started, so I've been reading a couple of weeks for the last year. I'm a computer architect on an AI. And then I realized, like, the papers, this is pretty typical. Like, here's some kind of math equation, and I realized I don't know what that means, or that, or that, or that, or that. But yet I build computers that run AI, right? And one of the reasons is, and this is partly the abstraction layer, there's mathematics that describes how they calculate the forward pass, which is interesting. What's more interesting is on the backward pass. How do you take an error in the output and then distribute it across all the weights and all the matrices so that you could slowly train the model to do something that's wrong, right? But it's actually doing, it's creating layers of association that are properly weighted. So there's information stored in a very distributed way. But the math on the one side all turns into A equal B times C plus D. And that's something a computer architect knows how to do. Adders, subtractors, multiplier, divider, whatever, squared. There's not that many operations. And then the key is to look at Math operations are not only defining operations, but also the data types and how the data is organized. And it turns out AI programs are mostly small. They're literally hundreds of lines of code. These hundreds of lines of code generate massive amounts of computation. And the program itself makes a graph, and it. I'm not sure what's going on here.
So when you press that, it becomes a slider so you can fast forward multiple slides.
Yeah, that's really not a great idea. All right, there we go. And once you have a graph, then you can execute multiple parts of the graph in parallel. So we, just community, our research works for me. We did like a search. We started looking at all these different models. Said, what are the fundamental operations and what are the fundamental graphs? It turns out the graph space is wide. And so AI researchers, some of it's very simple. Here's a graph. Here's an input, step 1, 2, 3, 4. There's other more complicated graphs. Here we have data flowing linearly down the pipeline, but it's also exchanging data. And we've seen almost every kind of graph. So with very small amounts of programs, you can define graphs that have very interesting data flows through them. Okay? And that's one of the complexities of AI. On the other hand, the number of operations in an AI graph is really small. Fundamental operations are matrix multiply and convolution. It turns out there's a method to turn convolution into matrix multiplies, which we do in TENSTORRENT. There's something called ReLU and its variance, which is basically a thresholding effect. You do a calculation and then it gives you a nonlinear threshold. Softmax is basically take an array of numbers and find the biggest one, but not just the biggest one, the biggest couple sorted with, and then you normalize it with a fairly steep gradient between the biggest and the smallest. Attention is the method of taking data and then describing a relationship of each piece of data and the input strings to each other. And then have to use a dot product, but we think we can turn that into multiply. And then there's something called tensor modification, which is loosely, you have data in one format, like one size matrix, and you want to put it in a different size matrix. One big matrix, bigger, smaller, square, go from 2D to 3D shape. And it turns out this small number of combinations, coupled with essentially random graphs, makes AI execution. So, and then the interesting thing is, when you go to build hardware for this, what the people want is very high clock rates. Right? And there's a lot of AI startups. And what we realize is all AI startups say, we're going to find this chip, a lot of operations, a lot of memory bandwidth. We're going to take the top 2 AI programs, hand code it to make it go fast. And then we're going to start to build the chip that will solve the pile of that turns out. And it's interesting probably because, well, if there's only 5 operations, like why is that so hard? So, and TENSTORRENT, it's also been hard for us. We've been working on this project for 5 years. We've actually written something like 5 complete software stacks about how to do this. From the first one, relatively naive and simple, we worked through the problem layer by layer. Right. It seems like, from an application point of view, there's PyTorch programs, there's big data, data prep, there's something called machine learning optimizer, there's metadata management. Like, so the application layer is pretty straightforward. Very technical. All right. And then in the data center, like it's pretty obvious you want data center, fast memory, fast storage. And then everybody wants to jump down to the fun part, which is building silicon that runs really fast with a super high clock rate. And then that mostly won't work out. So we started thinking about, like, let's really take this problem apart. I'm going to walk through a little bit about how the software stack is built and then about the hardware. Go up to the application layer. we focus on PyTorch and TensorFlow. Most of the other, metadata management, data prep and stuff runs on standard x86 servers. There's a software layer that's available called TVM, which is intermediate representation. So a programmer will program in PyTorch or TensorFlow, then we'll translate that into an IR, which looks like a high-level graph. In our software stack, we expand that graph so they can see every single operation and every single dimensional application. And then we do, as a graph modification, what's called autograph. So the graph is defined by the programmers, the forward pass. The autograph is the backward pass that says, how do you take the error at the output and distribute it across all the layers of the graph? Then we do a graph lowering step that says, take the big objects, like there might be a matrix multiplied to 1,000 by 1,000, and break that into pieces small enough to run on our AI processor. Then do a buffer insertion step. And then this is literally, we do a placement. So just like when you're building RTL, so you write the RTL, you synthesize to the gate level library, and then you run for placement and routing, distribute those gates in the best way on your chip. We take this graph, which has been turned into computation and buffers, and then we do a placement step that lays it out across a large number of processor cores, right? And then we do a kernel compile and a data flow compile to hook up those computations. Each layer of the software stack has been carefully defined so we can run this independently. And then we build a simulator environment. So when you come out of TVM, we can run and simulate, make sure we captured your program properly, get the correct answers at the high level. So we do the graph expansion autograph with another simulator to have now the forward pass, the backward pass, and that's somewhat lower graph works. Then we go down here and then we run a performance model and look at the number of cycles for each operation. And that's a little bit, if you're a gate level designer, all the library cells are characterized about timing and size and everything. And that information is used when you go to the placer step. Right, so we take the performance model information and that actually feeds into the placement. We say, these two things take a lot of cycles, we want more cores. These two things are right next to each other, so you want that to be really tight. These don't talk to each other, so they can be further apart. And then there's a low-level model that simulates exactly how this works, which you can only do in small cases without us using it. But each layer, we have something that's both functionally correct, and starting here, we have something that's cyclable. And just to, here's an example code. This is literally part of BERT. So BERT is one of the big language models. And if you go look at the graph, there's query, key, value, dropout. That's right at a high level code. And the interesting thing about this is the whole BERT program is something like 300 lines of code. It generates thousands of layers of matrix multiply those fundamental hops. We turn this into a graph, and here's a little piece of it. There's a fully connected layer, which is a matrix multiply, an element-wide add, which is probably an implementation of ReLU, a fully connected layer. And then we can take this big thing, and from the performance calculations, calculate how many cores we want to lay down. So TenStorrent processor, the current ones have about 120 processors on them. So you take a really big computational thing and put it on a lot of processors. You take a smaller one and you put it on less processors. You line them up so that the data, when it's finished computing here, flows to the next one. But if you go look at how an AI graph is instantiated on a TenStorrent chip, it looks like you've really taken RTL, synthesized it, and laid the gates out on each other. Except here, these are teraflop, computers. But, there's 120 of them on there. That makes sense? We've turned, and a friend of mine pointed out, the process we've been going on through is a little like what happened with emulators. So it used to be write a Verilog program, which is going to model a computer, possibly a typo computer, right? So when you simulate the Verilog program, you actually simulate it on a regular CPU one line at a time. But when you want to do an emulation, you synthesize it in the gates. Now you're going to place those gates across arrays with FPGAs, right? And then in the early days, getting that to run functionally correct, be debuggable, repeatable, and run at high speed is very difficult. It took something like 10 or 15 years for that software stack to get to the point where you could take an RTL model and reliably synthesize it. But we're doing the same transformation with an AI. And it's similarly difficult. The software stack has a lot of layers, and I just want to talk a little bit about an AI processor. Right? So we have inside the processors, RISC-V processors. There's math units that are really good at vector and matrix math. There's some data formatters. There's a local memory that keeps all the operands there. There's a data mover, and then there's bus interface. It's actually a fairly simple computer. And here's a block package diagram of what's in intensive for. Some of you guys did. There's 100 of these processors hooked up on a chip. So data can flow in from the bus interface, goes into the local memory, it's a megabyte and a half, and this holds local data and also buffers for processing in and out. Then we have something we call the Unpacked data formatter. So we can take an AI, basically a piece of an AI matrix or vector, and then reformat its orientation so we can do all kinds of transformations of shift, transpose. We can change the precision. We can do all kinds of things there, and then send that to either the matrix unit or the vector unit. They have local registers so you can do simulation and usual programming kind of model. And then on the way back out, we can also do data transformations and precision changes. Put the data in here, and sometimes that data circles around like this, and then sometimes it gets sent out to the next processor. And then we have 5 small rich processors, and approximately one of them manages the data movement in the bus interface. 2 of them manage the unpacked and packed streams. One of them manages the matrix unit, and one of them manages the vector unit. And then in our new chip, we also added a vector unit to that RISC-V processor, which can do special small programs. The big math units are very high performance but high latency. And sometimes you want to run a program that's a lot less operations but very low latency. And then in the standard SoC methodology, building the top level SoC is building those regular blocks. You have a PCI Express controller block, which has a 5 controller bus interface. Memory controller interface that has a 5 controller bus interface. And we have a very large NOC that hooks everybody together and instantiate a very large array of AI processors. And then there's a couple of special blocks. There's a boot processor, security. There's some extra bits for boot and then power manager. But the top level of the SoC is pretty straightforward, but it's a really powerful chip. And then the other interesting thing is in AI, these things run for hundreds of thousands of cycles on matrices. They're relatively insensitive to latency. We care way more about bandwidth on the NOC, bandwidth of the memory controller, than we do about latency. We built the processor. Okay. And we're building the next generation now. But we're going, this says 4 nanometer. I think that was the hope. It's actually 6 nanometer for Blackwell. We've doubled the processor count. We've raised the frequency of PTA targets quite a bit. In our next generation part, we've put a big array of RISC-V cores. So in the first 2 generations, we had a small number of processors. Now we have a bigger array. And we think we're going to do a whole bunch of things with those. They can run Linux. They can do some data prep and network processing. But also we can have computation and the AI processors talk to those computers and then send data right back to them. And to finish with this crazy story. So We worked with some of the people at OpenAI, I know those guys. And they did this project, there's some, OpenAI calls it Codex, and there's a project called Untitled. They took a language model, and then they took all the programs on GitHub, trained an AI model. And then there's a video online, I recommend watching it. It's really, great partner, I think. They, in real time, typed to the language model and generated the code from it. And it's an RT library, go build some test benches. Ridiculously easy to create some test benches. Today is very good at, if you write code, there's a lot of structure around formatting data structures. It just generates all that stuff off of it. And we think over the next couple of years, we'll generate more and more of our code straight from an AI model. And then we decided we are going to attempt to build a small risk processing parallel using the same technique. So the description of what we want to do will look like natural language. Here's the list of instructions, here's the pipeline structure, here's the operations we want, here's what patch works. And we'll start seeing how we get to generate that. Really interesting. And one reason I'm quite curious about it, first it's going to change how we build computers. The other is when humans write code, a little voice in your head, you're thinking, I'm going to do this, I'm going to do that. It's sort of a serial flow. One thing AI computers are really good at is parallel association. They can relate many things to many things. But when we teach the AI models to write code, they're going to write code in a very parallel way. And then that's going to impact how we build computers that run it. So I'm going to tell you some pictures of our computers. So this is a 4U server with 1, 2, 3, 4, 5, 6, 7, 8 Graceful cards. We can put 2 Graceful chips on a card for about 300 watts. So this is up to 16 processors. And then our team showed here in front of our first cloud. So we're building a cloud with about 2,000 Graceful chips in it. And we decided to build it ourselves because it's a really interesting learning exercise. How do you pull it? How do you power it? How much network bandwidth do you need? How do you get high performance storage? We have a micro storage server which does 130 gigabytes of bandwidth into a 4 processors. So that's up and running at Colorado and Austin. Possibly building cloud maybe still here for our next generation. And that's up and running. And we also build, there's OpenStack software that's on top of this. There's multiple layers of software outside of the AI space. So when you want to access AI, it's a whole bunch. Right. So kind of looking back, the transistor count has driven us. Well, it's enabled us to build faster computers, which is enable us to build really complicated computers. And then there's this process of how do you build abstraction stacks and set yourself up so you can actually successfully build complicated. Now, it's super important to know how your design fits together. And then, like, what part are you playing? How does the whole thing work? And that enables it to be successful. And then, my guess is the big data centers today are mostly regular computers with AI accelerators. Over the next 10 years, that's going to go to something like 80% AI. And then the AI computers and regular computers are going to work together. And then the AI computers can generate code that what we think is regular processing run. And that iteration is going to happen really fast. Really right. Oh, any questions? Wait a minute. Yeah, I can hear you, and I can repeat the question.
You mentioned yeah, quality.
Who's gonna run you right
Hi. So I want to first thank you for the presentation and the work that you've done. It's amazing. So I have a lot of questions and I'm not a computer architect, so please be a bit patient.
Okay.
There are three companies which I mostly follow regarding the chips they launch. So Apple, Intel, and AMD. And though I don't understand the architecture too much, but I look at the performance numbers and the scores. And I have noticed that recently Apple launched the M1 chip and it killed the competition because the idea was we don't need maximum compute power all the time. So they went to this big little architecture where you have some efficiency scores and some performance scores. And not only did they give amazing performance, they also cut down on the power consumption. So like it's an ultra low power and ultra high performance chip. Then recently Intel launched the Alder Lake series of chips, where again they also try to emulate the same kind of architecture. They had this efficiency and performance scores, but instead of like Apple is going for the ARM, which is sort of a RISC computer, whereas Intel still uses the complex instruction set computers. So what I noticed that even though the performance that Alder Lake is giving is like almost 50% higher than that of M1 Max, still the power consumption is 3 times. And now Intel is talking about this C5 you mentioned. It's basically a RISC-V computer based company. So do you think Intel is going to completely move to C5 or they're going to continue with this RISC architecture? And if they move, because I think power consumption is an increasingly more and more important factor nowadays, especially with mobile computing and all the edge devices. So I don't think the way RISC is going, can it like really compete with the RISC-based computers?
Yeah, so there's a bunch of different questions, so let's take it apart a little. So at the top, you're asking a question is x86 less efficient than RISC?
Right.
The answer is something like 5 or 10% better to be a RISC processor like ARM or RISC. It's a small number. The reason is inside, once you fetch the instructions and decode, inside the computer, they're all RISC computers. Intel processors, AMD, ARM, they're all out of order. They have what they call micro-ops, which are essentially large decoded versions of RISC. That's the first thing. The second thing is there a fundamental efficiency difference between Intel's implementation and like Alder Lake and Apple's? Well, you have to remember, Apple's a 5-nanometer die, and the Intel processors, they call it 10 nanometer. It's about the same geometry as TSMC 7. So there's a big efficiency difference because the Apple chip is a generation ahead on technology. So the third piece of your question is, there's a big little thing. Is that a good thing to do? And the answer is, when they first started doing it, no, because they didn't know how to put the fast stuff on the big ones and the slow stuff on the little ones. There was a bunch of complexities in scheduling. But a small processor, you make a trade-off about speed versus efficiency. So if you want to go very fast, you're willing to pay the power bill. But when you're going slow, you want to save the power. And Apple got very good at that. And I think, and then I'm just looking from the outside now. I used to work there, but they're able to take their applications and in the application and operating system say, this should be on the big core, this should be on the small core. And iOS really fine-tuned to use the right processor for the right thing. I think Windows is more, let's say, generic. It says I got stuff to do. What should I put it on? It's not as good at figuring out which core to put it on. So I don't believe with Windows that they're getting the advantage of the big little stuff as much. And I think they're working on it, but it's a different thing. Having the processor design and the operating system, those teams work very tightly. And also Windows, they have to support Intel and AMD, they support multiple generations. Apple, when they come out with a new generation, there's a very targeted version of the operating system for that processor, and they can do lots of optimization. Now, the question you didn't ask is, in a mobile chip, there's a CPU, there's a GPU, and in Apple chips, there's actually a very large AI. And they are ahead of everybody on putting more of the transistors in that chip to AI. And that's because they anticipate more and more AI applications in client and mobile applications, which I think is true. And I think at some point when you take the lid off a chip, you're gonna look inside and see that half of the transistors are for AI, even in a mobile chip. Now in the data center, I think it's gonna be about 80%. The AI applications are, as we get more transistors, it's going to take over all this. Did I answer your question?
Yeah, thanks.
Yeah, that's a good question. Any more questions? Yeah, you want to grab the mic?
Can you hear me?
Yeah.
So my question is from the perspective of whether the software ecosystem, especially the tools and the frameworks, right? Are they maturing fast enough to actually catch up with the advances in the company? With the shift towards the multi-core processor architectures, I've been following this, right? Like as software developer.
Yeah,
the software developers struggle to really kind of architect and design the application software to really take advantage of multi-core. Now with the GPU, the compute and everything, much of developers actually really narrowing the gap, or is it actually kind of widening?
Yeah, so here's a fun story. So the VAX 800 that I worked on started in 1982. It was a dual processor. It was two VAXes in that box, about 3,000 watts. And they had a group in the Fortran compiler team, 4 people, and their plan was to build a parallelizing compiler so that when we ship that product, you could have a switch and say, compile this Fortran program on 2 processors instead of 1, run twice as fast. And they started that project in 1984, and it's not done yet. Right? It turned out automatically parallelizing code is really difficult. Right? And so when people run these multi-core processors, sometimes you just have lots of threads, and that's kind of nice. And then something like in HPC world, they use a layer called MPI, and they say, I'm going to coordinate. I'm going to take a big problem, break it into pieces, and coordinate it. And there are some problems that are naturally easy to multi-thread, like finite element analysis. You take an object, you break it into a bunch of pieces, you say, give the first 10 pieces to this processor, the next 10 pieces to this one, right? GPUs was very parallel. You get 1 million pixels on the screen, you have 1,000 processors. So you basically say, first shader gets these 1,000 pixels, next shader gets these 1,000 pixels. So they had what I call given parallels. There's parallelism naturally in the program, and it was easy to get that acceleration. But if you're trying to write complicated Java or C, and then you say, I just want this to be parallelized to go faster, that problem is not generally solved. There's some framework. Like search was really interesting, because Google figured out, hey, I have this huge database. When I do a search, I can put a fraction of the database on a lot of different computers and parallelize the search. It's a fantastic thing. They did something called MapReduce. So they could map the problem to lots of processors and reduce the answer. So there's been problems that showed up that it was naturally parallelizable. But we haven't made much progress on non-parallelizable code. Now on the AI space, just in a few years, like when we worked at Tesla and built a autopilot computer, Café was a popular thing. And about halfway through that, there's lots of limitations in Café. PyTorch came out, and TensorFlow at Google. Since then, now there's new applications. So the AI space right now is evolving fairly rapidly. But we still write C and C++ programs. They're really good at what they do, right? And then some people move, there was JavaScript and Perl, but then the world really likes Python, right? So that's pretty stable. So periodically, there's a big step forward in either productivity or libraries. There was a whole bunch of languages developed to do, like web pages and stuff. And some of them were around 6 months, some are still around now. Yeah, software evolves kind of when it needs to, but some problems are really hard. Paralyzed is really hard. People can mostly describe what they want for AI, but compiling to a large number of GPUs is very difficult. And it typically takes lots and lots of programmers to get the performance. Because they're hand optimizing the real problem. That's good.
Thanks.
Back.
So I have a simple question. Many of the times when we work with
Yeah, hold the mic up, I can hear you.
NVIDIA-based graphics part, deep learning model training is. So many times we observe that the utilization is around 50%, and most of the time is spent in data transfer from CPU to the GPU and all this. So, do you think it is because of the inefficiency in the way we are handling the libraries, or can it be done better by redesigning the hardware?
Yeah, so the question is basically, when you look at an AI model running on a GPU, you see a lot of time spent passing the data.
Passing the details.
Yeah, so currently, and I know NVIDIA is working on this, but when it first, the way the computer model for GPUs is there is a computer, which for most PCs is AMD or Intel processor. And then there's a PCI Express slot, and then the GPU sits there as an accelerator, right? And the application, the game, everything runs on one of the CPUs, and then certain calls are passed to the GPU, right? So you give a buffer and a command list, and then the GPU accelerates certain operations. But the fundamental model is there's a processor, there's data structures, the application runs on the CPU, and then you're passing stuff back and forth. The GPU is not running as a standalone computer. Now that's been enhanced a lot. But like when you run a PyTorch program, it's not really running on the GPU. It's being interpreted on the CPU, and then data is being passed back and forth. So some of the data moving around is caused by that, and then there's a whole bunch of people working on trying to optimize that. And this is one of the places where if you have enough people, they really know how that driver works, how the GPU works. You can optimize out some of that data weight, but it's actually somewhat difficult to do. And then if you want to scale up a large number of processors, it gets more difficult. So one thing we're trying to do is build arrays of chips where all the data is put on AI processors. And then they have local CPUs that basically can interpret some of that stuff and keep all the data in the AI thing. So we don't spend so much time on the data. So there's partly a software model, there's partly how the applications work, and then there's partly like how do we build the hardware and the drivers for the future to do that better. And people are working on it. It's a real problem people are working on.
Is it similar to MapReduce?
Is it similar to?
MapReduce?
No, not really. Well, so Google, when they built MapReduce, they invented a bunch of things. There's this thing called the big file system, MapReduce. They figured out how to distribute a lot of data. So when you're doing searches, the data actually is striped across a large number of processors. So what's actually going back and forth is your search commands and results, not parts of the model or images. So they're trying to move as little data as possible by distributing the data. And so they solve that problem in a different way. That's an interesting question. Any more questions? Good. Thank you for that.
Yeah, we have a question
Oh. Where?
on that.
Yeah,
I don't know what's in it.
Can you just click on the Q&A? On the top right. Why don't you click?
All right, can you share your view about some of the key challenges they have, like data acquisition, storage challenge, and how irrelevant data is handled? I'll start by answering part of the question. So today, people think of AI as a big data problem. You have a massive amount of data, like language database, image database, and then you train AI models with lots of data. But that kind of makes sense. But it's kind of interesting because humans don't learn that way. Right? Like when my daughter turned 16 recently and learned to drive a car, and I taught her to drive a car in about an hour. I did not feed her a million hours of video, right? There wasn't hundreds of people labeling streets for her. Right? Maybe she's a genius, I don't know. But I mostly gave her, there's about 20 rules to drive a car. You know, stay on the left, don't hit anything. You know, speed up and slow down as gradually as you can, stop at the red things. Wait for oncoming traffic before you turn. Like, there's not that many rules, right? Right? And then there's some muscle memory about if I turn the steering wheel a little bit, it turns a little, if I turn it a lot. Oh, and it, you know, how much you turn the wheel depends on how fast you're going. So you practice in a parking lot, and it takes about 10 minutes to get the muscle memory for the brakes, gas, steering. For most people, I have friends actually never learned to drive, but and that's because she's actually, you know, smart. She has an intelligence in her head. Right? And she has some life experience of seeing roads and cars. But like I know my daughter, she wasn't spending a lot of time staring at how people drive. When she was in the car, she was on her phone listening to some story, right? So I don't think she has that many hours. And then there was they built an AI model that learned like Go, right? Which is a simple set of rules, but it's a hard game. And there's two ways to do that. You could have taken all the winning moves from the best players and had a big data approach to training Go. Or you can make a simulator that knew the rules of Go and then had the simulator play another simulator, right? And they essentially start by making random rules, right? But the winning rule gets trained into a model. So here's two methods. One is you have 100 gigabytes of Go moves from winning games. You can train them all. The other is you have 9 rules in a simple C program, and then you randomly make moves. If the simulator knows which one wins, and you slowly accumulate winning answers. And what they found is the AI models trained that way got better and better. And then that model with no data won to be a human world-class player. That's a simulation method, right? So, and people are starting to do simple things like you can build a game engine and simulate driving cars around, and then have the car do random stuff, but when it runs into something, say that's bad, and that's what you want, that's good, and then train an AI model for that. So in principle, we could build a simulator that learn to drive a car with no data. People are starting to work. There's projects that train robots to do stuff without any data. Robots just try different things and then they slowly figure out what works and train models. So there's a really interesting thing. So there's big data problems. If you have good data sets, you can train AI models. So language models are trained with big data. Like some image recognition is trained with big data. But there's things already being trained with simulation. Now imagine you have an AI model that knows what an object is. It can actually make a simulation of the world and start to train it. So people are starting to work on it. So there's little kids when they first start to see the world, first it's fuzzy. And then psychologists think they start to recognize objects, and then object permanence, and then object movement. And that's sort of trained with data. But once you start to get that data, most of what you learn is your thinking. When you go to school, the teacher talks very slowly, very slowly, about once a day, so that's something interesting. Right? But then you think about that, you do some problems to learn. The data rate in school is very low, but the thinking you do actually is very high. Now, the irrelevant data thing, there are people who worry about it. If you scrape the internet for all the language, inside that is boatloads of formatting characters and junk, but they're actually starting to train AI models that strip all the irrelevant stuff out. You can recognize what's language and what's important and not important. But I think mostly the irrelevant data stuff is going to be an AI model that processes data. And they're starting to do that with image training too. If you're trying to train a big image set and like a third of the pictures are your cute, cousin or something, it's a bad training set. So they're saying it's redundant, this is irrelevant, this is duplicate, this is fuzzy. But that stuff is. What are the challenges of real-time AI? That's a really cool thing. Does anybody here ever works on real-time systems? So when computers are really simple and you write a simple program, you say, I want to do these 20 steps and it happens. Steps later. But if you write a big program and then you run it on an out-of-order computer with a complicated memory, the variance in how fast that runs is really high. It becomes, for a real-time system, unreliable. And then what happens a lot of times is you have to over-specify the computer to keep the program simple, or it'll be too slow sometimes. And AI has that problem. If you run an AI program in a GPU, and it's a really complicated program, the timing of it's really random. Now, the way we build AI processor is we turn the program into a graph, and then we lay the graph out really carefully. And we've actually built some models that run time-wise very consistently, which is what real. So some of the method of real-time is consistency. There's actually two. All right. That's that. One last question?
Thank you, Jim. And actually, this kind of program, I just want to thank everyone who attended and don't continue like going forward also. The government of Telangana is very aggressive initiative. Actually, telecasted live right now. And by the tsat, and we really want to thank tsat also. And Photonics Valley Corporation. These three initiatives that we want to go continue in future also. Every expert coming to India or online that we want to help going forward. So Veda is partnering with the Telangana government and tsat and Photonics Valley Corporation. Thank you. I really want to thank everybody.
So, do you want to take a picture?